We're going to rip its ass open in a few minutes. It's going to just die in a corner, crying somewhere in Mexico. Or something. Good morning, fellow mathematicians. Welcome back to another video. Once again, finally, after such a long time, it's once again time for
Papa Flammy's random week.
Oh yeah. Can someone please play Freude schöner Götterfunken to celebrate this opportunity for you guys to see some more amazing problems? No one's playing Freude schöner Götterfunken, never mind. We're going to skip that part. Fuck you, editor. Whew. So, today I would like to start this awesome week off with this monster right here. That's called Leibniz Integral, and I really only know of one way to solve this bitch boy right here. You can probably also solve it using complex analysis, I really don't care. We're going to use the Leibniz rule for integration on this one, Feynman integration, how many people also like to call it. And let's go through the thinking process of solving this thing. Well, it would be nice to get rid of the square root right here because, well, integrating square root stuff also in the denominator isn't quite cool. So it would be nice to kind of get the square root x squared plus 2 in the numerator somehow, so that they cancel out. And well, there are ways to do this, because if we would just like to introduce a parameter, for example a t, into here, and make this thing, this integral, a function of t, well, then we could just differentiate it using the fundamental theorem of calculus, and well, then we would be fine. So why not differentiate this thing right here with respect to t? So that also means I prime of t, so the differential of that thing, is nothing but integral from 0 to 1. And at this point we can use the special case of the Leibniz rule for integration because, well, upper and lower bounds are independent of t, so we can interchange this integral sign and this differential and turn this into a partial derivative. And also, this whole 1 over stuff is not dependent on t, so let's bring it in front. So we end up with 1 over x squared plus 1 times square root x squared plus 2 times the partial derivative with respect to t of this chunk right here, inverse tangent of t times square root x squared plus 2 differentiated, integrated with respect to x. Okay, and that's why I made this trivial video on how to differentiate this thing. I'm not going to go into further detail, I'm just going to go ahead and differentiate that. So that's the integral from 0 to 1 of 1 over this chunk x squared plus 1 square root x squared plus 2. And now, what do we have? Well, at first we have square root x squared plus 2. And you see, this is going to cancel out quite nicely. Over 1 plus that argument squared right here, t squared x squared plus 2. Integrated with respect to x. And well, what you can do now, we can just factor this stuff right here out, and well, then we have a final expression for now for our I prime of t. That means we end up with dx over, now we have x squared plus 1 times, and this is just t squared x squared plus 2t squared plus 1. And integrating this isn't quite easy, so that's a job for partial fraction decomposition, and that's going to be an outtake. So I don't want to bother you with those small little details, that's why I'm making outtakes. I hope you like this little bonus video concept here on the channel. So I've written everything out, partial fraction decomposition, blah blah blah, bringing the 1 over t squared plus 1 term to the outside, and now we have this thing right here. And well, one of those two integrals is really quite easy to integrate, because this first one right here is nothing but the inverse tangent of x from 0 to 1, and well, inverse tangent of 0 is just 0, so that cancels out, and inverse tangent of 1 is going to weigh to pi over 4. Use your calculator, Wolfram Alpha, do it in your head or something, I really don't care, it's quite easy to calculate. And now we have this thing right here, and we would like to bring it into the same form as this one right here, so 1 over x squared plus something. But you see, this little t squared term right here, this coefficient is bothering us. So why not factor this term out right here? So if we factor that out, let's bring it to the outside, we have t squared over t squared. That's going to be a 1, so that also gets rid of this thing here in the numerator. Coolio. And well, all we have to do is to divide this last term right here by t squared. But we are not completely done yet, because this right here was in the form of x squared plus 1 squared, you could say. So we have to bring this into a form of something squared. So why not take the square root of that thing and square it right again? So that would make things easier. And well, now we know how to evaluate that. I made several videos on that. I'm using it all the time. So this thing right here is going to evaluate to the reciprocal of this square root term. So square root t squared over 2 times t squared plus 1. And now inverse tangent of, and now x over the square root term. So this is going to evaluate, well, square root of t squared is just t. So this is t times x over square root 2 times t plus 1. Evaluated from 0 to 1. And well, if we plug in 0 into here, that's going to vanish, so that's quite good. If we plug a 1 into here, well, what is this going to be? This thing right here is this coefficient. And also we have this inverse tangent of t over square root 2 times t plus 1. That ain't looking good, but it's going to get better in a few minutes. So right now we can conclude that I prime of t is nothing but. So we have this pi over 4 right here. So we have 1 over t squared plus 1 times pi over 4. And also we have this negative. Don't forget your negative sign right here. That's important. So we have 1 over t squared plus 1. And now we have this square root of t squared. That's just t. So let's bring it here. And down here we also have to multiply by square root 2t squared plus 1. Okay, and we have the inverse tangent of this chunk. So inverse tangent of t over square root 2t plus 1. And that's looking really ugly right now. But I want you guys to encourage yourself and try it out to integrate this. It's not too hard, because we have to integrate this now. We want to get back to our I with respect to t. And don't forget, if we would let t approach 1, that would mean we are going to land at our original I, Ahmed's integral, the thing that we wanted to evaluate. But also we would end up with a constant. To get rid of this constant, we would like to find another bound that would make things easier. And we are going to choose infinity as the upper bound. You're going to see in a few minutes why this is the case and why this is the best choice at all. So we already came pretty far, my boys and girls, and don't get fooled by this weird expression. We're going to rip its ass open in a few minutes. It's going to just die in a corner, crying somewhere in Mexico or something. So I'm not quite sure if you could follow what I was saying before. That's why I wrote out everything. I just want to make all the steps clear for you guys. So you see, that's our original integral, and that's our parameterized integral. And you see, if one of the integral bounds, when integrating this chunk right here, solving this initial value problem, would be 1, well, we would just be back at Ahmed's integral, our original one. Okay, nice and fine, but what about this weird infinity stuff I was talking about? Well, the good thing is, if we would let t approach infinity right here, positive infinity, that means our inverse tangent would just go to pi over 2. So we would just need to deal with this weird rational function right here. So that's the plan, and we are going to continue now. So, like I said, we want to take the integral from 1 to infinity. That also means we have I. So just integrated this thing right here with respect to t. I, when t approaches infinity, minus I of 1, but I of 1 is just Ahmed's integral I. And also we have a right-hand side, so we have to integrate this also. 1 to infinity dt, 1 to infinity dt. Okay, so evaluating this is quite easy. Pi over 4, you can bring it to the outside, it's constant. This is just the inverse tangent from 1 to infinity. Inverse tangent of infinity goes to pi over 2. Inverse tangent of 1 is pi over 4, pi over 2 minus pi over 4 is just pi over 4. So this thing evaluates to pi over 4 times pi over 4, which is just pi squared over 16. Whew, that was a mouthful. And now we've got this bitch boy right here, and we are going to call it J for Jens, the mathematical mean guy. And you see that kind of right here looks like our original one. So it would be absolutely crazy to kind of reduce this weird looking integral to just this one right here. Or maybe also to this one, we will see in a minute. So we are going to deal with this now in a proper way by introducing a nice substitution. So let our t be equal to 1 over u, and this substitution is extremely helpful because it means we can get our original bounds back. You will see in a minute why. That also means that dt is nothing but negative 1 over u squared du. And we can plug all of this information into j. So j is now nothing but an integral going from, well, you can also turn this into u being equal to 1 over t. Well, if we plug in 1 into t, it just goes to 1. And if we let t approach infinity, well, u goes to 0 in this case. So that's quite nice. And, well, what else do we have? Plugging all this 1 over u stuff in. So we have 1 over u squared plus 1 square root 2 over u squared plus 1 inverse tangent of 1 over u over 2 over u squared the square root plus 1. And then we have negative 1 over u squared du. And you see we can use this negative sign right here on the integral to change the upper and lower bounds. So we now have the integral from 0 to 1. We are back at the original bounds. Woohoo! That's already quite awesome. And what else do we have? Well, we have this 1 over u squared part right here. So at first I want you guys to notice if you would factor out this 1 over u squared on the square root, we end up with 1 over u on the outside. So factoring this out. So we have 2, 1 over u, square root of 1 over u squared is just 1 over u. I hope you can see where this came from. But if we factor that out, we also have to factor it out on this one right here. So 1 over just u squared in this case. I'm terribly sorry. So you see, with this one right here, we are basically back at this expression right here. And you can do the same spiel right here. So that's quite nice. If we factor out this 1 over u squared right here, that's quite a mess. We end up with a 1 right here plus u squared. I hope you can see where all of those steps came from. And the nice thing is we have this 1 over u term right here in the numerator. It's going to cancel out. Same spiel here. 1 over u squared is just going to go to hell pretty quickly. God damn it, my chalk. That's the only long chalk I have left. I'm so often out of chalk. So that already reduced quite nicely. You can do the same thing here if we factor this out. We have this 1 over u right here. We have this 2 and we have this u squared right here. This and that is going to cancel out. Just take a piece of paper, try it out for yourself. Right now we are back at an integral du over 1 plus u squared times 2 plus u squared inverse tangent of 1 over square root 2 plus u squared du. And that's really amazing because that is basically what we had right here. That's really basically it. So that's absolutely cool. And well, now I would like to just make use of an identity I have derived before, because we have the inverse tangent of 1 over u, you could say. 1 over a function of u. And you know, we can take the inverse tangent of x, add the inverse tangent of 1 over x to add, and get pi over 2 if our x is greater or equal to 0. And you see our u is exactly in the interval from 0 to 1, so that's positive. So this right here exactly holds. So we are going to end up with, we can solve this right here. That means that pi over 2 minus the inverse tangent of x is nothing but the inverse tangent of 1 over x. We are going to make use right here of this fact. So at first, we are going to end up with an integral from 0 to 1. And now we have du over 1 plus u squared square root 2 plus u squared. And now we have this chunk. Pi over 2 minus the inverse tangent of, and now taking this argument, taking the reciprocal, you could say, square root 2 plus u squared. Integrated with respect to u. Maybe I'm going to write it right here. And we already came pretty far. I'm going to write out everything and then we are basically done. So we are actually done with the worst part of it all, and the rest is going to be nice and chill, but we don't want it to be too chilly, because, you know, cold things aren't good for flammable things. Otherwise the flame of mathematics is going to vanish right here on this channel. We don't want it to. Never mind it. That's not funny at all, so let's continue this bitch boy. So, you see, the cool thing is, this right here is our original I. So that's what we wanted to evaluate, and just like I said before, we reduced it to Ahmed's integral once again. So we have I right here. And like I said before, if t approaches infinity, the inverse tangent is just going to be pi over 2. So that thing right here is nothing but I when t approaches infinity. And now we can basically just solve for our I right here. And then we are close to being done. So adding I on both sides, subtracting this stuff on both sides, we are going to end up with 2I being equal to, okay, now we have 2 times I as t approaches infinity minus pi squared over 16. And well, now we can divide both sides by 2 because it's not equal to 0. That's going to be 32 right here. That's going to cancel out. So we end up with I, Ahmed's integral, being nothing but I as t approaches infinity minus pi squared over 32. And now the big old question is just, what is this right here? And we're going to evaluate it now. So I as t approaches infinity is nothing but pi over 2 integral from 0 to 1. And well, you know the rest, it's just this stuff right here. So dx over 1 plus x squared, square root x squared plus 2. And I'm going to make this next substitution in outtake because differentiating this thing is quite stupid. But you can introduce other substitutions. You can do integration by parts. It doesn't really matter. I'm going to shorten this process a bit. We would like to introduce a substitution, v being equal to the inverse tangent of x over square root x squared plus 2. And well, if we differentiate that, that also means that dv is nothing but, that's going to be in the outtakes, 1 plus x squared square root x squared plus 2. And you see the dx right here, don't forget that. This whole thing right here is just our dv. So we are going to end up with pi over 2. And now we have an integral from 0 to 1. If the inverse tangent has a 0 right here inside the argument, well, this is just going to be 0. And if we have 1 in here, this is just a 1 over square root of 3, and this is going to evaluate to pi over 6. Use your calculator or something. And dv. Integrating dv is quite easy, so we have pi over 2 times v from 0 to pi over 6. And this thing right here is just, well, pi over 6 then, in this case. So we have pi squared over 12. And now we can just plug this into here, and then we are done. So, Ahmed's integral I is nothing but pi squared over 12 minus pi squared over 32. And that's a nice value. Do I have to? Yeah, I'm going to simplify it. Well, we can multiply this by 3 over 3. And we can multiply this by 8 over 8. That should work out. This is going to be 8 pi over 2 minus 3 pi over 2 is 5 pi over pi squared. I'm sorry, not pi over 2. And this right here is 69, if I'm not mistaken. 96 would be better, but well, that's it. We are done. That has been Ahmed's integral, and you know, that basically is just part 1 of a monster of an integral. So there was already quite some work, and that's not even the start of what you are going to see at the end of the week. I thank you guys for watching. If you did enjoy this video, please like and subscribe. Please share those videos everywhere. I would appreciate all kinds of support from you guys. My channel has become 1 year now today, so that's a 1-year-old boy. I'm quite proud that I've reached such an amount of subscribers in such a short amount of time. Parasinical reference. Never mind. If you want to support the channel a bit more, buy my stupid ass t-shirts. Actually, I really like this one. I'm wearing this in public. It's really quite cool. Or do support me on Patreon. And up until the next video, tomorrow, have a flammable day. See ya!